And we are recording. Let's see. No Cook is here. Have Melton, right? Okay. Let's see. Morning. Good morning. Abigail? Where? Oh, yeah. I'll get that eventually. Morning. So that's Larissa, correct? Okay. Andrea? Why do I always want to think you're Andrea? Maybe I should wear my glasses. All right. How about Kincaid? Gotcha. Kincaid is here. Mullins? No. Lewis? Cooper? Hunter? Gotcha. Crowder? Not yet. Reinhardt? Gotcha. No. Rogers? Let's see. Kennedy? Madeline? Yay. Got one right. Hughes is online. Let's see. Galloway? Durgan? Gotcha. Were you the one that doing, what was it, economic biology? Is that your hardest course, or is that somebody else? It is? Okay. I'm trying to picture not just names and faces, but when you, for those of you who've done the All About You quiz, I'm trying to remember who's who. Spade. Gotcha. Burton is online. Kinder is here in person. Jones? No. Canterbury. Kraus. Got both. Hobson? No. Ray? Fisher? Guess not. Still got about 2 minutes and some change, so I'll do some announcements before I go back to or reminders, more likely, or more accurately, before we go back to 10. So by Sunday, you should have 10 points of independent work. That's one announcement. A reminder, I should say, things I've been saying. So make sure you get some done. So even if you only write one paper and say you get 5 points over the weekend, obviously you've only got 50% of where you should be, but that's okay. Next week, just do 15 points and you'll be caught up. The point is, some of you haven't even started writing papers, and you need to start. Like I said, you need 10 points by Sunday. Speaking of writing papers, a lot of you have started. So more so than any other semester I've had before. So this is the best start to a semester I've had yet, which is good. It looks good for you guys, but it makes me a little bit slower to grade. So please forgive me for being a little bit slow to grade because I do have a lot to grade. And also yesterday my priority was lab 1, because that's due today. The lab we did this week is due today. So I wanted to go through and grade as many of those as I can. And that's still my priority today is grading lab 1. What else? Your pre-lab for lab 2 is due on Sunday as well as 10 points of independent work. I think that's it for reminders. So make sure you're signed into your WVSU email account. We've been having some issues with this. So one of the people who've been having issues, she met with me yesterday online and we figured it out. And then for those of you who had lab with me on Wednesday, saw that even I had an issue. I was signed into my Google account, but then when I went to open up a document, for some reason, I wasn't signed into my Google account. So make sure you're signed into your Google account if you're having problems opening a document, because that might be it. Or if you're having problems joining this meeting, because you can see somebody tried to join earlier and it wouldn't let them because they weren't signed into their WVSU email account. So make sure you do that. What else? Make sure you're on time to lab. Make sure you're there. What else? I don't know. These are all reminders, nothing new. Does anybody have any questions about anything since this is our first weekend before independent work is due? All right, let's go back to attendance then, since it is almost 8. Abigail is here. Kincaid is here. Andrea is here. Bless you. Mullins is not here. Lewis is here in person. Cooper is not here. Hunter is here. Caleb Melton is here. Crowder is not here. Reinhardt is here. Isabel Melton is online. Minter. Julia. Rogers. Talbert. Kennedy. Gotcha. Kennedy is here. Hannah is not here. Larissa's here. Madeline is here. Hughes is online. Marquis? Marquis is here. All right. Cook is here. Durgan is here. Tate Spade is here. Burton is online. Kinder is here. Jones is on. Jones tried to get online. No, not here though, and not online currently. Canterbury? No Canterbury. Prowse. Did I say that right, Prowse? Oh, no. So, yeah, I'm looking for it. So you're Christopher Crowder. Yeah. So Tristan is not here. Christopher Crowder is here. Julia, correct? Julia is here. It's now past 8 o'clock. So in the future, guys, try to be here on time. We're all running behind. Not just you guys. I'm still taking attendance. So yes. Okay. Yeah. Thank you. Yeah. I appreciate the reminder. And let's see. Jones. Canterbury. Oh yeah, Jones was almost online. Canterbury. Tristan. Hobson. Ray. Fisher. Wait, no, that's Hannah, right? Fisher's not here yet. Hannah is here. Last name Hannah. Okay. Anybody didn't call? All right. Before I jump into chapter 2, I'm done with the announcements, which were basically just all reminders. Nothing new there. So, does anybody have any questions about labs or independent work? Nope. All right. Let's jump back into chapter 2. Oh, yeah, one more announcement. This one actually is new information. So when the weather starts getting better, it is possible that we could have class somewhere else, but we'd all have to agree on it. So start thinking about that if you'd be okay with it. Like maybe we all take our computers and go sit outside, when the weather's nice. So think about that, and I'll ask that question when the time comes. So the question will probably be like, would you be okay with going outside for a class every once in a while? And if not, would you be okay with us leaving you behind and you watching the class online and things like that? We'll cross that bridge when we get there. Anyway, any questions about anything? One last time before we jump into this. All right, so we're jumping back into chemistry. Whoops, let me back it up a little bit. Went too far. Last thing we were talking about is what an atom is made up of, right? We talked about how atoms are made up of protons, electrons, and neutrons. I think one of the last things I said you needed to know was, the thing that a lot of people get messed up is this relationship between protons and electrons. And I was saying, and we're going to talk about this in more detail later, and we're going to really cover it in lab next week. When something gains an electron, it becomes negative. And the reason I think that's hard for people is because, when you think of getting something, mathematically, when you gain something, that's usually a positive, right? That's a +1. Just like in this case, you have one more electron. But the problem is electrons have a negative charge. Therefore, when you gain an electron, you become more negative. And again, another thing that confuses people is when you lose an electron, you become more positive. So try to keep that in mind. Any questions about the mass and the charges of these subatomic particles, these things that make up an atom? All right. Oh, yeah. Obviously, here I am talking about charges. But if an atom has where the protons equal the number of electrons, and then it is neutral. It does not have any charge. And in this class, as far as we're concerned, every atom that we talk about is neutral unless otherwise stated. Like if I say how many electrons does carbon have, which is something we will talk about later, you should be able to know because I didn't say how many electrons does a +1 carbon have or how many electrons does a -1 carbon have, right? If I don't specify what charge it is, then that means it is not charged, which means, well, we'll come back to what that means a little bit later. Let me see what that noise was really quickly. Does anybody have any questions about this slide while I check out that noise? Okay, good. Oh, yeah, that reminds me. So the first word for attendance will be, let me get this pulled up here. Let's say, whoops. The first word for attendance will be gold. So for those of you who are in person, again, you can send one email at the end with all the words for a little bit of extra credit. For those of you who are online right now, send a picture of something gold. A picture of something gold. So not gold, not the word gold, but send me a picture of something gold. That's the first word for attendance. Anyway, any questions about all this? This stuff is pretty basic. You've probably had this in high school science classes. So anyway, we're still talking about the atom. The atom is basically made up of a nucleus surrounded by some stuff. But first we'll talk about the nucleus. The nucleus is the central core, and this is where you can find the protons and the neutrons. And you need to know that. That might be a test question. Actually, it probably will be a test question. What do you find in the nucleus? Protons and neutrons. Not electrons, because electrons are moving around the nucleus, and we'll talk about that in the next slide. So on the inside of a nucleus are protons and neutrons. Don't forget that. That would definitely be a test question. Or, I guess I could word it, where do you find protons and neutrons? And the answer is, you find them in the nucleus. One thing your book doesn't talk about, I'm only going to briefly mention it, because as far as this class, it's not important. But, well, actually, this part's a good little review. But what charge does a neutron have? Good, neutral. It's in the name, right? Neutral. What charge does a proton have? Positive. Good. Now, what happens when you try to put two positive things together? Do you know? Think of like a magnet when you try to put two magnets at the same thing. What happens when you do that? They repel, right? They repel each other. So look at this. And this is this uranium. This is just one example. Uranium has 92 protons all squished together really tightly. And think, they don't want to be together. Those protons are repelling each other. So you have to imagine it takes a lot of energy just to keep that nucleus together. And that's basically what nuclear energy is, right? So if you were to split this, whenever you break a bond, even if it's a nuclear bond, and that's not the proper word, but as far as we're concerned, it is. If you were to try to split that, it would release so much energy. Now, that isn't something you need to know because, again, we're not teaching nuclear physics in this class. But that concept will come back throughout the semester. That thing where I just said however much energy it takes to keep that thing together, that's how much energy would be released if you were to break it. And that is a concept that will come back throughout the semester. So, again, you don't necessarily need to know what happens when you split an atom. But, yeah, we'll come back to that. Any questions? Also, let me put it next to this. This is just uranium. That's just an example. The idea here is that protons and neutrons are found in the nucleus. So any questions about that? All right. If you came in late, make sure you send me an email at the end of class to tell me you came in late. Otherwise, I won't remember and you just have no credit for today. So here's another picture. This is from your old textbook. This is another way of looking at an atom. This one only has 2 protons and 2 neutrons, but there's the nucleus and there's the 2 electrons. And I like this better than some of the other pictures because a lot of times they have rings, which is what we're going to use in lab, and we'll cross that bridge when we get there. But I like this picture because it's a cloud, because technically they don't move in rings. I'm going to teach it that way because that helps you learn other stuff. But in reality, just so you know, it's more like they kind of orbit all over the place. And this cloud represents where an electron is most likely to be found. Right, and you can see it's darker here and like lighter out there. That's because those electrons would be more likely to be found in here and farther out there. You don't need to know that for this 100 level course. I just wanted to point it out. So, any questions so far? All right, the periodic table of elements. There it is. I'm going to be providing you with it a lot. I should say a lot. I'll be providing you with a periodic table a couple of times. You will not need it for any exams. You should know how to use it basically, and I'm going to show you how to basically use it and what it does. But again, there will be no questions. I'm not going to ask you what the periodic table is, so you need to be able to use it, but there's not going to be a question where I ask you if you know things about the periodic table. Anyway, that being said, let's talk about it. The periodic table includes atomic number and atomic mass of each element, which we're going to talk about here in a second in the upcoming slides. It provides key information about the properties of the elements. We don't even talk about in this class, but yeah, basically, and if you've done some of those videos I've shared with you, you know some of them. But you can tell, like if something's lined up in this particular column, we know all those things have one, similar chemical properties. I won't get into it too much, but yeah, that's why this table is the way it is. Like all these in this line have something similar chemically. All these in this line have something similar chemically. So that's why it is set up the way it is. That's the Cliff Notes version. Not that you're going to need to know that, but now you do. Periodic tables also show how electrons are organized. I'm going to walk back over there. Basically, again, going from left to right. So the ones all the way on the left, they have 1 electron on the outermost ring, which we'll talk about in a second. And the ones next to that have 2 electrons on the outermost ring. If you look at it the other way, starting from right to left, the ones all the way to the right have 8 electrons on the outermost ring. And then you move 1 step to the left and they have 7, so on and so forth. Again, these aren't things you necessarily need to know. The periodic table provides important details about how atoms will react with each other. That's an important bullet point not to memorize. If you're taking notes, you don't need to write it down, but that's a good preview to some of the stuff we'll be doing in lab next week. I'm going to be giving you the name and the symbol of an element. And from that, you're going to be able to figure a bunch of other things out, like how many protons does it have? How many electrons does it have? How many electrons does it have on its outermost ring? How many chemical bonds can it form? You're going to be able to figure all that out by using the periodic table and me telling you the name and the symbol of the element. Anyway, any questions about this slide? All right, there's another picture of the periodic table. So again, they're all, it's built this way for a reason. It looks random, but it's not. Anyway, and we're going to come back to this idea, right? So this is what you're going to need to decipher. You don't need to memorize anything, but if I were to show you this without all these little labels, you should understand what it is. If I show you this picture and say, what does the H stand for? Of course, now you can tell it's the symbol because it's there, but in an exam, you won't know that. So that's the symbol. This is the atomic mass, which we're going to talk about in detail moving forward. The name, that's very self-explanatory. And the atomic number, which again, we're going to talk about moving forward. That's it. Basically, again, you're going to be able to use, you're going to be able to need to use a periodic table and be able to decipher something like this, which is what I'm going to guide you on later. Speaking of which, let's talk about it. Atoms of an element have the same unique number of protons. That's a big one. You definitely need to know that for the exam. Atoms of an element have the same unique number of protons. For example, we'll use this one right here. Helium, every single helium in the universe has 2 protons. I know that for a fact. I can say that confidently. The reason I know that for a fact, I can say that confidently, is because, and this is another way to write it down if you want, there's different ways you can describe the same thing. The number of protons defines the element. That's how I know that every single element in the universe, every single helium in the universe has 2 protons. Because if I take away one of those protons, by definition, that thing is now hydrogen because it lost a proton. Not that you need to know that specific example. Likewise, if that helium that has its 2 protons were to gain a proton, and go back up here, see, here's the helium, it has 2. So if it gained, it would have 3, therefore it would be lithium. So yes, this is very important. Know that. The number of protons defines the element. Another way of saying that is if you change the number of protons, you change the element. Matter of fact, that's going to be a theme. There's going to be at least 3 questions worded that way in the exam, most likely. If you change the number of protons, you get what? And the answer is a different element. If you change the number of electrons, you get what? And I'll tell you that when we move forward. If you change the number of neutrons, you get what? And I'll tell you that moving forward. So yes, right now, that's what you need to know. If you change the number of protons, you change the element. Also, the number of protons happens to be the atomic number. Right? So that's right here. When you're looking at the periodic table, that's what that number means. It's the atomic number. It tells you how many protons it has. But that'll be important later too, because even though it's not on here at all, like the word electron is not on here anywhere, is it? Nope, just being sure. Okay. Number of electrons is not here. But again, you'll have some questions, especially in lab, where I say, all right, how many electrons? I might give you just this and say, how many electrons does helium have? And I didn't say a charged helium, right? I didn't say it was a +1 helium or a -1 helium. I just said a helium. And again, like I said earlier in this class, if I just say an element's name, you can just assume it's not charged. So therefore, again, if I say this has, how many electrons does helium have? You look and say, oh, it has 2 protons. And he didn't say anything about being charged. Therefore, the electrons and the protons must match. So helium has 2 electrons. Of course, the Cliff Notes version of that, the hack, if you will, is the atomic number, as far as we're concerned in this class, also equals the number of electrons, unless otherwise stated, right? So if I say, again, that it has a -1 charge, that means it has an extra electron. If I say it has a +1 charge, that means it's missing one of those electrons. But again, unless it has a charge, then the atomic number not only equals the number of protons, but it also equals the number of electrons, which will be important a little bit later, and you'll see why. So any questions about what the atomic number is and what it means? The element symbol, that's self-explanatory, right? And again, I'll never ask you to memorize that. You will not get a test question where I say, what element is He, right? Or what element is C? I won't do that. So if there's no questions about the atomic number or the electrons, also let me put a big X to this, just as a reminder that helium is just an example. I'm not going to ask you specific questions about helium. Matter of fact, it's a great example because it's such a small element, but it's not really useful in this class. In biology, we will never use helium in our discussions unless it's just an example. So anyway, if there's no questions about that, let's move on to mass number. And let's see, mass will be the next word for attendance. So again, if you're online, instead of sending me the word mass, take a picture or send me a picture of mass. And that could mean a couple of things. And I'm doing that on purpose. Is the idea, well, I don't want to tell you why, but anyway, send me a picture of mass, please. The rest of you here in person, you can send me these words at the end of class for extra credit, a little bit of extra credit. Anyway, let's talk about the mass number. The mass number, and this is where the math gets involved in this class. I told you there would be a little bit of math in this chapter. Here it is. The mass number is the sum of the protons and the neutrons. Another way of saying that is, and I'm going to abbreviate here because it's really hard to write like this, protons plus neutrons equals the mass number. It's really horrible. It's hard to do. There we go. And from that, you will have some basic, I guess you could technically call it algebra, but I don't know. It's not complicated. For example, I might say something like, this element has a mass number of 14. Actually, I have to write it down. This random element has a mass number of 14. It has, that is so hard to read. It has 7 protons. How many neutrons does it have, right? Basic math. 7 plus what equals 14? 7 plus 7 equals 14. So those are the kind of math questions you're going to get in this chapter. It's a really good effort to record and stream them. If you miss class, you still have it. It doesn't work. So I'm not guaranteeing you any of this will ever work. So if you miss class and this doesn't work, then you're just out of the points. Good time to remind you of that. These are here for your convenience. They're not guaranteed. Anyway, now that we're back to the mass number. So again, we are talking about mass number. Now, something a little bit different. It's called atomic mass is similar to the mass number, except it may differ on the occurring. Great example: helium. Types of helium in the universe that we know of. You can see it up there, but there's H1 and H3. They have different names. But your regular old helium mass is 1. This other one has a proton and a neutron.
So its mass is 2. Has 3, right? It has a mass of 3. 2 neutrons. Now, if you were to look up at the periodic table, if you were to look at the atomic number, the mass number of hydrogen, but if you were to look at the atomic mass, it's 1.00784, which, if you're not paying attention, might indicate to you its mass. Like if you were to take a hydrogen, you might think, oh, a single hydrogen has a mass of 1.0, but that's not the case, because this one is a lot more abundant in nature, in the universe. Therefore, the number is actually really close. So it's an average. I'll come back to this concept here, and then I'll take questions. And that brings us to the next word you need to know, and you definitely need to know this for the exam. It's called isotopes. You need to know what an isotope is. Going back to the way I said it earlier, I said if you change the number of protons, you change the element. So now I'm telling you, if you change the number of neutrons, so again, different number of protons, different element. Different number of neutrons, isotope. Electrons. They also behave identically in chemical reactions. Not that I'm going to ask you any of that, but they have different number of neutrons. To this, hopefully you do remember that, but even if you do brain that, you'll be fine for the rest of the semester. But you need to know that an isotope is the same element. It just has a different number of neutrons. I'll also put a next from your textbook, because I'm not going to add the difference between carbon 12, carbon 13, and carbon 14. Those are just examples. There you go. So yeah, again, for the exam, what you need to know, it's the same element, it just has a different number of neutrons. So, which related between and the atomic mass. Right, so the mass of carbon is 12.0. Remind you, this is really important for the grand scheme of the semester. But I don't know. I like making sure you know. If you were to look at any carbon in the universe, not one of them is going to have the mass of 12.0. Either have 13 or 14. If you take the one in the universe and average them together, that's where we get the 12.11. Does that make sense to everybody? A Cub Scout group, and you had I don't know, or maybe it's Boy Scouts, I don't know, whatever. You had 7 people who were 12 years old. You had 3 people who was 13 years old, and you had 1 person. Right, so you do 12 7 times. You would do 14 1 time, and then you would average. And you would be closer to 12 or 14, but it wouldn't be exactly 12. It would be 12. Blah, blah. Does that make sense? All right, so that's the atomic mass. And again, I'm going to put it next to this just to indicate I'm not going to ask you how many neutrons does carbon 14 have. Well, yeah, here's a picture, but it's a fake picture of a real thing. Over exaggerated. How fingers? What's the average number for fingers for humans? Does anybody know? Like what's the average finger number? Especially based on what I've just been telling you. That's a good hint. Average number of fingers. 10, right? 5, you would think. I would say the hand or 10 fingers on both hands. Add all the fingers, like he said, and it might be something more than 10, because like in this picture, this is a real condition, a fake picture of a real condition. Some people have extra fingers. They also have extra toes. So, right? It's probably a little bit above or a little below. Some people have extra fingers. Some people have fewer fingers. Actually, who is out and the number is 10. But that's my point with this, right? There are no carbons that have 12.011, right? This is carbon's nature. Finger toes. Radioactive isotopes. I'm really going to go through this one. Questions about radioactive isotopes. Isotope. No. The only difference is it's radioactive, right? It's unstable. That's all you really need to know. Not that I'm going to even ask you that, but just so you know, they decay, right? So remember I was telling you about all that, the energy holding the nucleus together, those protons and the neutrons? Well, it doesn't last forever. Those, long story short, and even though I'm not going to ask you about it, all it takes for these things to decay is I'm looking at how many, right? How many carbon 14s? Not that you need to know that. As a matter of fact, I was about to say, are there any questions about this? But I'm not even going to take questions. If you have questions about this, ask me later or talk about it. I do give you some more examples from your old textbook that kind of explains how carbon 14 or carbon 12 dating works. But I'm not going to ask you any questions about it. It's there. You can learn about it if you. It has its limitations if you want, but I'm not going to test you on it. Important, slightly important for the exam, really important for next week's lab. You need to understand. As far as we're concerned in this class, it's only the electron involved in the chemical reactions. Electrons. Because in this class, we really simplify. It really helps. Another way, let's get a little bit more specific. You need to know this right here, this bullet point. It's the number of electrons that determine chemical properties. Hinting at the periodic table over there. All the ones in that column, they have one electron on their outermost ring. Every single one of them. Because of that, they behave similarly. It's that number of. Here's something else you really need. And this is unrealistic, but for the sake of this class, this helps. You know, you're going to draw the neutrons in the nucleus, and then we'll draw a ring, right? That first ring holds electrons, and as you can see, the ring holds 2 electrons, and that little line's. We're concerned, this is not true in these labs and exams. After the first one holds 8 electrons. And for the exam, the first ring holds 2, and then once it's filled, it goes to which holds 8. And filled, as far as we're concerned, it goes to the next ring, which also holds 8. As far as we're concerned in this course, the next one holds 8. The thing your book pointed it out is that say it holds 8 electrons. What I mean is, 4 pairs. Like they do travel in pairs. Like there's 2 there. Wow, that is so hard to read. 2 there, 2 below the screen where you can't see it, 2 there. But yeah, for your purposes, it does not matter that there's 4 pairs. Just know that there's 8 on the outermost ring. There's 8 electrons. So for the lab, it has a full outermost ring. Of course, you can't have a full outermost ring without having a full innermost rings. It has full rings. It is stable. It's not reactive. Not need to get any more electrons. It doesn't need to give any electrons away. It has a full ring. It doesn't react with any other atoms. Any other atoms. Yeah, it's happy, so to speak. And that's why we have chemical reactions, because sometimes when they right here. They do need more electrons, or they do need to get rid of some electrons, right? They need to share electrons, get all kinds of different things that we'll talk about. But if they don't have a full ring, that's what makes them chemically active. Now they want to hook up with some other atoms because they need to do some stuff with their electrons. Keep them together, and we'll talk about that later. So yes, again, I just described right here. This ring, as far as we're concerned, holds 8 electrons. To get a full outer ring. Just trying to have a full outer ring. But before we dive a little bit deeper into this concept. All right. Molecules and break new ones. It's not going to question, so if you're taking notes, there's no. This is more like, why are we even talking about this? It's biology, not chemistry. Well, that's why. Constantly. Chemical reaction. Not that you need to know this, but again, since I already talked about it earlier, if you have a uranium that has those 92 protons in the nucleus and you split it, and it starts losing, right? Because once you lose protons, you're a new element. That's a nuclear reaction. The elements haven't changed. It's just the way they're rearranged, or they're hydrogen peroxide. How many of you ever use hydrogen peroxide? You got a little cut and put some. So what happened? Yeah, it burns a little bit. What's it look like? What happened? Right? And here's why. Not that you need to know this, but putting hydrogen peroxide on it, probably not pure, but we won't talk about that. It has some chemical reactions happening, and hydrogen peroxide turns into water and bubbles, right? Air and water. So that's what makes the bubbles. Anyway, here you can see 1, 2, 3, 4 oxygens. 1, 2, 3, 4. On that side, that's what we have. And then after the chemical, we have 1, 2, and 1, 2, 3. We still have the same atoms, right? That still weighs the same. Still have the same atoms. The problem is not the problem. So now we have different molecules, but we still have 4 oxygens and 4 hydrogens. Does that make sense? All right. Another thing you definitely need to know, because I'm going to ask you, because I probably won't, but because I'm going to be using these words so often. Hard chemistry. So for us, even though this isn't always the case, for us, almost always, I think, I'm trying to think if there are any exceptions, but I really don't know. So as far as we're concerned in this class, the reactants are on the left. Another way to determine because there might be some exceptions in this. I know there's exceptions. I don't remember any exceptions in this class. Another way of saying that is the arrow always points away from important later. I'm not going to ask, there's not going to be a test question where I say, what's a reactant, what's a product? But there will be a test question where I say, do a chemical equation and say, how many oxygens are in this reactant? So obviously you're going to need to know what a reactant is. Another thing to mention, doesn't mention it, I'm not going to ask about it. Sometimes, very often, reactions actually go both ways. Not in this class. Class we keep it simple and the arrow only points one way, but in real reactant or the product, yeah, this right. Anyway, any questions about that side? This is one more important bullet point. This will be important later. Matter cannot be created or destroyed. Concept. If you're in a weight class, you already know that. Matter cannot. So in this chemical reaction, hydrogen peroxide, right, because we no longer have hydrogen peroxide itself, wasn't. The things that made up that hydrogen are still there. Were not destroyed. The hydrogens were not destroyed. So anyway, any questions about this? Okay. Let me back up before I talk about this slide. I'll remind you what I've told you so far. If you change the number of protons, you change the element. If you change the number of neutrons, you get an isotope. And now finally, the third one, this finishes the trifecta. If you change the number of electrons, you get an ion. You need to know that. If you change the number of electrons, you get an ion. Very important. Because when we talk about chemical reactions and chemical bonds, it's all about the electrons. So as you can imagine, we're going to be talking about electrons. So you definitely need to know what an ion is. So like I said, it gives you an ion. But also, if you're changing the number of electrons, you're going to have a charge, right? So if you were neutral and then you gain electrons, you're going to become more positive. If you were neutral, gain electrons, you're going to become negative. If you were negative and you lose some electrons, you're going to become neutral, right? So changing the number of electrons. I'll put a question mark to this. I probably have not. And I'm definitely not even going to use these words again. This is for, higher level biology courses. But yes, a cation is positive, and an anion is an ion that's negative. Again, I'm almost definitely never going to use those words in this course. Almost definitely never going to ask you about that. But your book mentioned it, so do I. Also, I might share a video with you where you hear the words cation or anion, and you're like, what are they talking about? So now you know. Anyway, the last thing, something called ions. And we're actually going to come back to this concept a little bit later too. But an ionic bond is the bond between oppositely charged ions. So if one atom gives up an electron and becomes more positive, and another one's gaining an electron and becomes, so we have a negative thing and a positive thing. What do those things do? They attract each other. And that's what an ionic bond is. Someone's going to miss that question, and it always makes me sad because I am going to ask you questions about all the bonds. But in my opinion, that's one of the easiest ones because it's in the name. Ionic bond. It's a bond between ions. What's an ion? It's an atom that's lost or gained electrons. It's my charge. It's in the name. Anyway, any questions about this? All right. Let's see. The next word for attendance, I'm going to write it, saying it. So if you're online and listening to the lecture and not watching the screen, there's the next word for attendance. And again, if you're online as opposed to in person, that is, it's backwards for you guys online, but you can see it. It's red. Anyway, so if you're online, send a picture of that word, right? Don't send the word, send a picture like that. Anyway, all right. Just whatever. Like I said earlier today, I've been prioritizing the lab. So a lot of you sent in the words on Wednesday. Haven't heard from you yet. That's why I did get the email. Return the email yet. So don't worry about that. Don't let that stress you out. But anyway. Here's a good example. This is one of the most common examples. Sodium. Right? Sodium has that one electron on the outermost ring, which is why it's all the way on the left side. Excuse me. Yes. Chlorine has 7 on the outside, right? So remember, they need 8 to be happy. Either gain 7 electrons, give up 1. Giving up is easier. Chlorine either give up 7 electrons or just gain. Gaining 1's a lot easier. So that's what happens. Sodium gives 1 up. And in this chapter, it's a side note to Not that it's important for the right now. If you mix it with water, it will explode. This is a poisonous gas that would kill people, right? So, by themselves, they're very dangerous, but change one electron, and now all of a sudden you have table salt, sodium chloride. It became negative. Chlorine gained that electron. Chlorine gave up the electron. Chlorine became negative. This is positive. This is negative. Think different charges attract each other, and that's what keeps them. And that's where we get sodium. Which brings me to an independent work topic if you want to look into it, because I want to look into it. Thing I've ever heard of it. I'm going to look into it. Alabama is about to be executed with nitrogen gas. And that's the first time in history that he's been executed with nitrogen gas, which is really confused at how that works. What is it? Oh, it did? This poor guy. I mean, I shouldn't. But first they tried to do lethal injection, and that didn't kill him. Like, let's try. Never done on anybody. But anyway, yeah, it's either happened or it's about to happen. But either way, then when you're breathing right now, 80% of what you're breathing is nitrogen gas. It's interesting to me that they can kill somebody with nitrogen gas when we breathe so much. Independent work while we're talking about chemistry. How does nitrogen gas kill somebody? Anyway, you can watch this little animation if you click on it. Instead of that picture that I just showed you, it's the same thing. How exciting, right? Covalent bond. Ionic bonds. There's 3 bonds we're going to talk about. We're done with one of them. Two. The next one is covalent bonds. Does anybody know what that prefix means? Co. Or let me ask you, that's too broad. No. If we were in biology class, like if we were just 2 people, they're cohabitating. What does that mean if people are cohabitating? Living together, right? They're cohabitat. How about a divorced parent, a divorce co-parenting? What does that mean? Share the responsibility. Co, as far as we're concerned, you should think of that prefix meaning share. That's not exactly correct, but for us, that's spot on. Covalent bonds are bonds where atoms share one or more pairs of electrons. Taking notes for this 100 level course, what would suffice? A covalent bond is when atoms share, put a line through this, electrons. That's enough for this 100 level class. Technically, and yes, technically there can be multiple numbers of, but if you're like taking notes that you're going to study for an exam, then that would suffice. Covalent bonds are when atoms share electrons. Another thing you definitely need, even way later in the semester, actually it will be, is covalent bonds are the strongest bonds. That will come back. We'll be done with chemistry for a while. We won't talk about it for a while, and then all of a sudden, boom, we'll be talking about it again. So keep that in the back of your mind. Covalent bonds are the strong. In chapter 10. I forget the numbers now since we're on a new textbook, but yes, covalent bonds are also the most common, but I'm not worried about that. You need to know covalent bonds are when they share electrons and they are the strongest. Also, not that I'm going to ask you this, but when they come together in covalent bonds, the term for that is that's a molecule. Right? So these pictures right here, molecule formaldehyde. That picture right here of something called casual dehyde. Technically, that's what we call it. Up every once in a semester. I accidentally, you'll hear me call any. It's one of my big mistakes. I'll call it a molecule. Now it usually is because covalent. Sometimes it's not. Sometimes it's an ionic compound. But anyway, that's what a covalent bond is. As always, is always the case with ionic bonds or covalent, just doing this, right? They're trying to fill their outermost shell. That's the point of these shell. So again, the key here is when we're talking about covalent bonds, they're sharing electrons. They're not giving them up. They're not taking them. They're sharing them. Covalent bond, like co-parenting and cohabitating. That's going to be slightly important, is to know that there's two types of bonds. Not to ask you how many types of covalent bonds are there, but you do need to know the difference between a non-polar bond and a polar bond. A non-polar bonds are shared equally. A bond is when they're not shared equally. That'll make a lot more sense when we talk about it later. I'll show you pictures. It'll make a lot more sense. But for now, that's just the introduction to that concept. Polar bonds, the electrons are shared equally. Polar bonds, non-polar bonds, they're shared equally. Polar bonds, they are not shared equally. All right. Here, this is a really good example because you're going to be doing this in lab. Here's a table you need to fill out. And you need information about carbon, right? So here's what we'll do. Give you the atomic number, or you're going to look that up because I'm going to tell you it's carbon. Periodic table. You're going to look up carbon and make, okay, its atomic number is 6. Then what do we know? How many? We know if its atomic number is 6, it has 6. Between those subatomic particles, it has 6 what? What do we know if its atomic number is 6? Or what is it? I'm not sure I heard you, but that's okay because we're running a little bit behind. It's number. Oh, actually, that's a good place to stop. So the last word at all, just send me your favorite movie or pick one that you like. Is the last attendance phrase. And remember, if you came in late, send me an email, please. You too.